Hi, today I'm going to walk you through some of our standard Novi Cloud outputs. Our model building and our data set generation creates many different data types and data sets. And I want to give you a flavor for some of those here today and how they might be used. So I'm sitting in Spotfire right now, typical Spotfire, but you can connect just about any business intelligence tool to Novi Cloud, just kind of a standard ODBC connection. And here I'm looking at is a pretty common plot that we look at, and I'll take a minute to walk you through it. On the x-axis here, we have profit in pounds per foot. So we go from 0 out to 2,000 out to 4,000. Um, Part of our standard outputs is we take total profit values and divide it by the lateral length. It's kind of a simple, feature transformation, but valuable. Each of these little panels is broken out by the formation that the well was drilled in. So I have 6 of the more common ones in the Delaware Basin here. Everywhere, everything I'm showing you here is out of the Delaware. Each dot is a well. So have in this case 1,600 wells. These are the wells that are bounded on both sides using our spacing features. And then on the y-axis, we have the percent oil uplift or degradation. And what that is it's a Shapley value, and these Shapley data is one of our key data outputs. And what the Shapley data shows you is how much that particular feature, in this case proppant values, impacted the well's prediction by pushing it above or below the average for the training data. So here you can basically see kind of there's a curve of these wells with very low proppant values getting big negative impacts on the prediction, and then as you get higher and higher, you see an increase in the Shapley values that's kind of slowly changes and becomes less and less impactful the more proppant in terms of pounds per foot that you get. So this is pretty similar to a sensitivity type chart that you would have for kind of a standard analysis. But the interesting thing here is that the model is picking up that essentially the different formations in the basin have different sensitivities to the proppant loading. You can see that the XY and the A lower both have a strong positive correlation all the way out to 3,000 pounds per foot, whereas the Bone Springs much more have kind of a diminishing returns type slope where you make it out to 1,700 or 2,000 pounds per foot, and it really kind of flattens out in terms of impact beyond that. So great that the model is able to learn this. Gives you confidence that it's working, etc. In this data set, these Shapley values, this transformed data, all of that is standard output for every single one of our model builds. Let me show you another version of that. Here we have position and zone on the y-axis. So we go from 1, aka it was drilled at the bottom of the zone, up to 0, it was drilled at the top of the zone. For each of kind of the 5 main formations in the basin there on the x-axis. So these wells down here were drilled at the bottom of the AXY. These wells here were drilled at the top of the A lower. And again, I'm coloring the dots or the wells by the Shapley value. And this is the Shapley value of the position and zone, essentially of the target. So these wells up here with the dark green got a plus 6% relative to model average on the oil production. The ones in the white and the orange are -1, -3% production. So the model is essentially saying, hey, it really likes these wells drilled up here near the top of the A lower. It sees there's a lot of benefit to the production from being drilled up there. The AXY, that sits right on top of the A lower. So this kind of high producing zone right here lines up with the high producing zone there at the bottom of the A lower, or at the top of the A lower. And the model doesn't actually know that the AXY goes on top of the A lower, so it's pretty cool that it's able to pick up on that. So switching gears to spacing here, on the x-axis we have distance to the closest lateral neighbor, and that's in feet. And we calculate over 50 spacing features. We calculate the distances in 3 dimensions to essentially all of the standard neighbors you would think about, like on either side, staggered neighbors, stacked neighbors. We calculate number of wells in the neighborhood, parent-child, distances to parents, how long the parents have been online, azimuth, a variety of different features. And but distance closest to lateral neighbor, that's kind of the closest thing to map view spacing that you're going to get. And here I have the wells in the Delaware Basin, and we have going from 500 out to 1,600 feet distance to the closest lateral neighbor. And I have that for both the left chart and the right chart. And on the left chart, what I have that spacing feature cross-plotted with is the actual oil that those wells have produced of 720 AQ. And looking at this, you get a good idea of why spacing is a hard problem to tackle, and that's because it's a scattershot. I mean, it's really difficult to look at that and figure out what the signal is, and that's because a lot of these wells here have large completions or drilled a bit of rock, so any spacing degradation that you see is kind of it's difficult to pick up, on kind of the broad scale. Over on the right, I have that distance cross-plotted with the Shapley value for that particular distance. And you can see that as you bring the wells closer and closer together, the model is saying that's responsible for degradation in its predictions. And this is just one of the Shapley values associated with this with one of our spacing features. There will be Shapley values for various other spacing features as well, for parents, for number of wells in the neighborhood, etc. So that's why we're in the single-digit percentage here. But I want to show you a pretty cool thing that you may be wondering why on that chart it looked like maybe there are some wells that had this kind of slightly different trend, and another set of wells that had a first trend. And here I have that same chart that was the purple over here, but I'm coloring it by the thickness of the Wolfcamp A. So in blue we have it's thin, so that's 240 feet thick. You see that's kind of around the margin of the basin. It's shaped like a dish. In red we have the thickest part, which is up over 500 feet thick in the deepest part of the basin there, and kind of that state line Lee Eddy County area. And the model is essentially saying there's an interaction between the thickness of the Wolfcamp, which is it's a good proxy for the thickness of the entire column or the thickness of whichever formation this was targeting, and the Shapley value, or the model's view on the degradation as a result of the spacing. So if you're in a thin part of the basin, you're going to get more spacing degradation than if you were in a thicker part of the basin. So if you were, looking at that Concho Dominator pad, that's down here in the thick part of the basin. That obviously that scared off a lot of people for dense development. But majority of the basin, they don't have the benefit of having that thick column that can support greater densities. So if you're developing some rocks over down here, or in the far western part of the basin, you would definitely be worrying about your downspacing. So we can also look at the impact on gas-oil ratio, not just the impact on oil. And here I have wells per section on the x-axis. So this is kind of taking our neighbor count variables and our parent count variables and rolling those up together. And here on the y-axis, I have impact on gas-oil ratio. Again, that's Shapley values. And for all this, we produce, it's not just one, we produce a value for every single time step that we make a prediction for. So that's going from 30 days out to 720 days as our standard. So I'm going to step through each of these different time steps, and you can see how our model essentially says that these tight developments over there on the right side of the chart see an increase in gassiness as you go through time. And so, and this is cumulative GOR, not just instantaneous. So the model has kind of learned that not only do these dense developments have propensities to have high gas-oil ratios, but that is something that actually increases through time. We also, kind of standard outputs. We have a GeoShap, which is a rock quality index, where you can kind of see where the hot spots are for the different formations, the sweet spots. And then just want to give you one quick sample of another standard output data set that a lot of people get use out of, and that's contributing wells or analog wells. So here I have a well on Parsley's acreage in the southeastern Delaware. It's a Wolfcamp A lower well, so our model made a prediction for this well. And for the most part, you see the wells that I thought were analogous are kind of located in that same part of the basin along strike, and then in a little bit down dip of where that was located. All the all the data I showed you is available both for PDP wells that our model is trained on, and also for hypotheticals. So a lot of great value you can get out of it. Thanks for listening.